Alright, let's work some example problems with resonance. A guitar can be tuned using harmonics. In this method, once you set the frequency of the low E string, you can touch that string lightly a quarter of the way from the end of the string and play it. At the same time, you touch the next highest string, the A string, a third of the way from the end of the string and play it. Then you tune the A string such that the lowest harmonics you hear on the two strings are the same. If you do this and the E string has a fundamental frequency of 82.41 Hz, what will the fundamental of the A string be tuned to? Happen to have a guitar here, alright? So if I touch my E string a quarter of the way from the end of the string, I get this harmonic. If I play the A string and I touch it a third of the way from the end of the string, I get this harmonic. And then I just tune the two so they're the same, and my guitar is tuned. Okay, so how do we work out the math and figure out what frequency my A string will have? Well, the basic idea is this. Alright, if I look at the harmonics on my string has these two endpoints, right? And the first harmonic looks like this, right? The string oscillates like that. The second harmonic has a node in the middle, alright, and it looks like this. It oscillates like that, alright? The third harmonic has two nodes in it, so I draw two nodes splitting up the string evenly, alright? And if I look at this, right, there's the length of the string. This node is at half the length of the string. For the third harmonic, I have one at 1/3 and 2/3 the length of the string. Oh, good, because one of our strings, the A string, we touch it a third of the string, a third of the length of the string away. Alright, so there's what we're going to be doing to the A string. If we go to the fourth harmonic, it has three nodes in the middle of the string, so it looks like this. Alright, and this divides the string up into four pieces, so if I touch it a quarter of the way from the end of the string, I will damp the third, the second, and the first harmonic, but the fourth harmonic will ring, and that's what I'm doing to my E string. So basically what I've said is, I'm going to play my E string and I'm going to touch it a quarter of the length, the string length away from the end. It will damp these lower modes, and then the lowest frequency mode that I will hear will be the fourth harmonic. So what I'm going to be hearing will have a frequency of 4 times the fundamental frequency of the E string. Alright? On the A string, I'm going to touch it a third of the way from the end. Alright? That will damp the first and second harmonics, but the third harmonic will continue to ring. And the third harmonic has a frequency which is 3 times the fundamental frequency of my A string. So if I make those two harmonics, if I tune my strings so that they're the same, alright, then I play the strings without damping them and you know, damping out some of the harmonics. What I'll find then is that the frequency of the A string then has to be equal to 4/3 times the frequency of the E string. And my E string has a frequency of, we said, 82.41 Hertz. So I multiply that all out and I get 109.88 Hertz. Alright? When we discuss the music section, we'll find out that actually the string, if we tune our guitar using equal temperament, should have been 110 Hertz. Tuning it by harmonics gets me close. Alright, so there's our answer right there. If I tune with harmonics, my A string will be tuned to that frequency. A 1 meter long pipe, open at one end and closed on the other, is filled with an unknown gas. We then use a frequency source and a speaker to look for resonances in the air in the pipe. Scanning the source from 200 to 500 Hertz, we find that in that range there are resonances at and only at 251.25, 351.75, and 452.25 Hertz. What is the speed of sound in the gas? Alright, well, we know that for a pipe that's open at one end and closed at the other, the fundamental or first harmonic frequency is V over 4L, right? There's this factor of 4 because when we're open at one end and closed at the other, right, we only fit a quarter of a wavelength inside our tube when we excite the fundamental. So the fundamental actually has a wavelength which is 4 times the length of the tube. Alright, so there we go. So the fundamental has a frequency of V over 4L. But unfortunately, we don't know if any of these are the fundamental frequencies, right? Maybe 251.25, that's the lowest one we found. Maybe that's the fundamental. But we only checked from 200 to 500, so we don't really know. What do we do? Well, we have these different harmonics. How are the frequencies of the different harmonics related? Well, we know that the frequency of the nth harmonic is just n times the frequency of the first harmonic. Also, we know that for an organ pipe that's open at one end and closed on the other, we only get the odd harmonics. So n cannot be 2 or 4 or 6. It can only be 1, 3, 5, 7, and so forth. So if I look at these frequencies, these have to be the closest possible frequencies to each other. We found all of them in that range, right? And so we can say, well, let's say this frequency right here is the nth harmonic. Let's call that one the nth harmonic. I don't know what n is, but I'll call it f sub n. All right? But this one right here, it's going to be n plus 2, right? It's just the n is going to be 2 bigger. It's the next harmonic, and we only get even ones. So if I have these two frequencies, I can say the difference in those frequencies, that's f of n plus 2 minus f of n. But f of n plus 2 is just n plus 2 times the fundamental. And n is just, the nth harmonic is just n times the fundamental. So this is just going to turn out to be the n's cancel out 2 times the fundamental frequency. So by taking the difference of those two, I will get 2 times the fundamental frequency. Same thing if I go from this one to this one, right? That difference will give me 2 times the fundamental frequency. And if you look at these, it turns out that they differ by, it looks like delta f is equal to 100 and 100.5 hertz, all right? So that tells me that the fundamental frequency is just going to be half that, right? So the fundamental frequency is going to be 50.25 hertz. All right, so what I did is I looked at differences in frequencies, and I determined from knowing the difference, I could find the fundamental frequency. All right, and that turned out to be 50.25. But remember, the fundamental frequency in a pipe that is open at one end and closed at the other is just V over 4L. So that means that V is just 4L times F1, which is 4 times 1 meter times 50.25 hertz, which then is going to be 201.0 meters per second. All right? So there is the frequency, the speed of waves. Now let's go back and imagine, what if my pipe was closed at both ends and I found those frequencies? Would I get a different answer? Well, if my pipe is closed at both ends, okay, closed at both ends. In that case, the frequency of the first harmonic is just V over 2L, right? Because if it's closed at both ends, I fit half a wavelength inside my pipe. All right, so it's just V over 2L. All right, and the frequency of the nth harmonic is just still n times frequency of the first harmonic, but now I get even harmonics. So the difference between the frequencies of adjacent modes is just going to be, you know, the frequency of the n plus 1 mode minus the frequency of the nth mode, all right? And so that's just n times f1. Or sorry, it's just f1, sorry. So the spacing between modes is just f1. So if I did this experiment and I got these same values, but my pipe was closed at both ends, then I would say, well, my delta f is 100 what did we say? It was 100.5 hertz. But now that's precisely my fundamental. I don't have to divide by 2. But what does that tell me about the velocity of my wave? I have to use this equation up here. All right, so velocity is now just going to be f1 times 2L, which is 100.5 times 2 times 1 meter, per second. So this just ends up being, again, 201.0 meters per second. So it turns out if I'd gotten those same frequencies on a pipe which was closed at both ends, all right, I would have interpreted them as being different modes of the system. My fundamental frequency would have been higher, but it turns out I calculate the same velocity for sound.